Greetings. This time let's try actually solving some differential equations. In a first order differential equation, assuming it's written as dy dx equals h of xy, or whatever other variables you happen to be using, ideally we'd like to be able to solve this by integrating both sides with respect to x, to cancel out the derivative with respect to x. But we can't just integrate something that includes y with respect to x if y itself is a function of x that we don't know yet. So let's not do that just yet. Quite a lot of the study of differential equations involves finding a way to manipulate this so we can do that integral, or some equivalent. And one special case that's often very useful is if this function of x and y can be rewritten as a function of just x times a function of just y, a function of just x and a function of just y, combined with multiplication or division, either way also works, then we can solve this by a technique called separation of variables. The idea is we want to get all the x's on one side and all the y's on the other side. So we just have something about y dy and something about x dx, and then we can integrate. To do that, we can start by multiplying both sides by dx. But then we have both x's and y's on this side. So we'll also want to divide both sides by this function of y. Or if it's already divided by the function of y, multiply to get rid of it. Whatever works. Simplify, and what's left is 1 over g of y dy equals f of x dx. Everything else cancels out. At that point, you can now integrate, because you would be integrating a function of y with respect to y and integrating a function of x with respect to x. So that can actually be done. Let's try out some examples. For instance, suppose we have the differential equation dy dx equals x squared over y squared. As before, the first thing we want to do is multiply both sides by dx. Actually, before we even do that, check to see if this even is separable. This does look like it's written as a function of just x and a function of just y combined with multiplication or division. So that suggests this can be done. Let's try it. Multiply both sides by dx. And also, we now have x's, dx's, and also a divided by y squared. So we'll want to get rid of that y squared by multiplying both sides by y squared. And let's see what's left. Reducing the dx's, reducing the y's squareds. So y squared dy equals x squared dx. At this point, we can now integrate both sides. Integral of y squared dy, we'd add 1 to the exponent, divide by the new exponent. And likewise, x squared likewise becomes x cubed over 3. And also, since we're looking for all possible solutions, we should include a plus c. This is an indefinite integral after all. We don't really need a plus c on the other side, because if we had two constants, let's say c1 and c2, we could just subtract c1 from both sides, and c2 minus c1 is just some other arbitrary constant. So we really only need to include the constant on one side. Then to isolate y, because what we have here is an implicit solution, in the sense that this equation does describe how x and y are related, but it doesn't give us y equals a function of x, which is what we want. So we would then want to isolate y. Multiply both sides by 3. That cancels out the 3 here. And we would get 3 times c on this part. But since c is just an arbitrary constant, 3 times c is another arbitrary constant. So we can just call this, let's say, capital C. And to get rid of the cube, we would take the cube root of both sides. However, we can't split up cube root over addition, so we would just leave it like this. Cube root of x cubed plus a constant. this would be our general solution. And as usual, if you had initial values, you could plug those in and find the value of c. For example, let's say we happen to know that x equals 0 and y equals 2 is a point on the graph that it has to go through. We could just substitute those in, let y equal 2, let x equal 0, and then we could just cube both sides to get rid of the cube root and get 8 equals c. So y equals cube root of x cubed plus 8 would be the specific solution going through that point. Let's try another example. Let's say we have dy dx equals y plus 2xy plus 3x squared y. This might not look separable at first glance because this doesn't look anything at all like a function of just y times a function of just x. But the important thing is we can manipulate it so that it is. Notice that every term here has a times y in it. That means we can factor out y, and we're left with 1 plus 2x plus 3x squared. And that is definitely a function of just y times a function of just x. So we can solve this by separation of variables. This is separable. So let's try it. As before, multiply both sides by dx. And we want to get rid of this y here. So we have just x's and dx's on this side. So let's also divide both sides by y. And that leaves us with 1 over y dy equals this quadratic, 1 plus 2x plus 3x squared dx. And we can continue by integrating both sides just like we did before. Integrate, integrate. And now what's the integral of 1 over y? That should be logarithm of y. And this is actually going to show up quite often. Anytime you've got equals y times a bunch of stuff, you're going to end up dividing by y, integrating, and you'll probably end up with a logarithm. So this is a very common sort of result in these cases. On the other side, we can just integrate this polynomial. 1 becomes x, 2x becomes x squared, 3x squared becomes x cubed. And again, because this is an indefinite integral, we want to list all possible solutions, so we'll include a plus c. That's an implicit solution. We want to get an explicit solution. We want to have y equals something about x. So how do we get rid of logarithm? We exponentiate. We raise e to the power of both sides. E to the power of the left side, e to the power of the right side. On the left side, exponential and logarithmic functions cancel out. On the right side, we've got e to the power of a bunch of stuff added together. And here we can make use of the product property of exponents. That if you've got e to the power of a times e to the power of b, you can combine that as e to the power of a plus b, but that also works in reverse. Addition inside the exponent can be split up as multiplication of the bases. So we can split this into e to the x times e to the x squared times e to the x cubed times e to the c. But again, c is just an arbitrary constant. So e to the power of an arbitrary constant that we don't know yet is also an arbitrary constant we don't know yet. So we may as well just rename that capital C. So this would be our general solution. And once again, if we had initial values, we could substitute those in for x and y, all the x's and y, and solve for c to find the specific solution. Let's try one more example and see where we can go. If we had dy dx equals, let's say, x plus y, can we rewrite that as something about just x times something about just y? Is there any way we can write that as, doesn't really look like it, does it? In this case, this is not a function of just x times a function of just y. There's no way to factor y out of everything, no way to factor x out of everything. No matter what we do, this cannot be written as something about just x times something about just y. So this equation is not separable. But it is a member of another category called linear. and we can take a look into how to solve linear differential equations in a later video. But the whole idea of differential equations is largely about categorization. You split up a differential equations into categories, and any differential equation that fits into this category can be solved using a certain method, or if it's in this other category, you use a different method to solve it. It's really sort of a divide and conquer approach. But if it's not separable, you can't use separation of variables. But there may be other methods that do work. One other example that I think is going to be useful, if we have dy dx equals x squared over y plus x cubed y. Again, this might not look separable at first glance, but notice that both of the y's in these terms can be factored out. And we're left with 1 plus x cubed. And since we now have y here separated by multiplication and or division, we can get rid of that y by multiplying both sides by y. So let's try that. Again, we want to start by multiplying both sides by dx. And in this case, we can get rid of this y in the denominator by multiplying both sides by y. That way the times y and the divided by y cancels out. And we're left with y dy equals x squared over 1 plus x cubed dx. Once again, integrate both sides. Left side is pretty straightforward. Y is just going to turn into y squared over 2. On the right side, though, this doesn't look like as straightforward of an integral. So we're going to have to pull in some techniques from calculus. In this case, I'm specifically noticing we have this function within a function here whose derivative looks an awful lot like something else that's already in the integral. So that suggests what method? U substitution should work pretty well. Let's try that. If we just set this function within a function to be u, and this works really well with a function within a function because U substitution is just the reverse of the chain rule. Then we take the derivative, we get 3x squared, and an x squared appears right here. If we want to find du in terms of dx, we can multiply both sides by dx. And usually I'd also isolate dx, so we can just have something to replace dx with. But I'm also noticing that x squared dx already appears here. So let's just isolate x squared dx by dividing both sides by 3. This tells us that x squared dx can be replaced with du over 3. So this whole thing becomes du over 3. This is just u. So we're left with integral of 1 over u du. And the 1 over 3 can be extracted out of the integral as a constant multiplier. And of course, integral of 1 over u is going to be logarithm of u times 1/3. We still have the y squared over 2 on the other side, and plus a constant because we want all possible solutions. At this point, we should also replace u with the original meaning, 1 plus x cubed. And there's our implicit solution. To get an explicit solution, all we need to do is isolate y. So we multiply both sides by 2. The 2 times an arbitrary constant is still just another arbitrary constant, so we don't need to bother with 2c, we can just call it some other c. And then to undo the squared, we would just need to take the square root. However, since again we want all possible solutions, a square root should include a plus or minus. So y could be plus or minus, since it's an even root. Square root of 2/3 logarithm of 1 plus x cubed plus some unknown constant as our general solution. And again, if we needed a specific solution, we could plug in initial values if we have some for x and y and solve for c. And while we're at it, also choose plus or minus depending on whether y itself is positive or negative. So that's the core idea of separation of variables. Usable anytime dy dx can be written as a function of just x and a function of just y combined with multiplication and or division. The only real problems it can run into is if the integrals, the functions you have to integrate, end up being very difficult to integrate. Or if the result is some complicated tangle of y and some complicated tangle of x that can't be easily solved for, can't be easily isolated. But even in such cases, you can at least write the solution in implicit form. So that should work for quite a large variety of first-order differential equations. Not all differential equations, but many of them. Many of the first-order equations. And so give that a try. While you're at it, also try drawing out the direction fields for these, because direction fields is good practice and also gives you a good visual idea of what's going on. So try out some more examples. We'll look into some more examples of other ways of solving differential equations next time. See you then.